What specific problem does your proposed Thyme method aim to solve in the context of multimodal large language models and image reasoning?
The proposed Thyme method aims to address the limitations of existing multimodal large language models, MLLMs, in effectively incorporating visual inputs into their reasoning processes. Specifically, it seeks to overcome the challenges associated with two prevalent approaches: thinking with generated images, which often suffer from quality issues and high computational costs, and thinking with cropping, which is limited to bounding box outputs and lacks multifunctionality. Thyme introduces a novel paradigm that emphasizes rich functionality, allowing the model to perform a wide range of image operations autonomously, such as cropping, scaling, and contrast enhancement, while also executing complex mathematical computations. Additionally, it employs an efficient end-to-end training strategy that minimizes costs and maximizes performance across various perception, reasoning, and general tasks, ultimately leading to significant and stable performance gains. By integrating these capabilities, Thyme enhances the model's ability to reason with images more effectively and autonomously, addressing the shortcomings of previous methods.
Can you explain in detail how the Thyme method operates? Please illustrate this step by step, starting from user input to the final answer generation.
The Thyme method operates through a structured pipeline that begins with user input, which consists of an image and a corresponding question. First, the model analyzes the input to generate a reasoning process, determining whether code generation is necessary based on the problem's complexity. If the model decides that code generation is required, it autonomously produces the relevant code for image operations, such as cropping, zooming, or contrast enhancement. This generated code is then executed within a secure sandbox environment, which handles formatting and variable definitions to ensure successful execution. Finally, the results from the code execution are returned to the model, which uses this information to continue reasoning and ultimately produce the final answer for the user. This iterative process allows Thyme to effectively integrate visual inputs into its reasoning, enhancing its multimodal capabilities.
Could you provide a simple example that demonstrates the inner workings of Thyme? Walk through the steps the model takes, including any image manipulation or code generation involved.
An example of Thyme's functionality can be illustrated through a task where the model is asked to crop a specific object from an image. Initially, the user inputs an image along with a question, such as, "Can you crop the apple from this image?" The model first analyzes the image and determines that cropping is necessary. It autonomously generates code to perform the cropping operation, specifying the coordinates for the bounding box around the apple. This code is then executed within the secure sandbox environment, which handles any formatting and variable definitions to ensure successful execution. After the code runs, the model receives the cropped image as output, allowing it to reason further or provide the final answer based on the cropped result. This process showcases Thyme's rich functionality, high autonomy, and efficient execution of image manipulation tasks.
What are the unique theoretical or practical benefits of using the Thyme method compared to existing approaches like image generation and cropping?
The Thyme method offers several unique theoretical and practical benefits compared to existing approaches like image generation and cropping. Firstly, it provides rich functionality by enabling a wide range of image operations, including cropping, scaling, rotating, and contrast enhancement, as well as complex mathematical computations, which surpasses the limited capabilities of cropping through bounding boxes. Secondly, Thyme exhibits high autonomy, allowing the model to autonomously decide on and execute necessary image operations without human intervention, enhancing efficiency and adaptability in real-time applications. Additionally, the efficient end-to-end training process, requiring only about 200 GPU hours for the SFT stage, significantly reduces computational costs and inference latency compared to the high costs associated with image generation methods. Finally, Thyme demonstrates significant and stable performance gains across nearly 20 benchmarks in perception, reasoning, and general tasks, indicating its superior effectiveness in multimodal tasks compared to traditional methods.
How did you validate or test the effectiveness of Thyme? Please describe the experimental design, datasets used, and the performance metrics you employed.
To validate the effectiveness of Thyme, we conducted comprehensive evaluations across nearly 20 benchmarks spanning 3 major categories: perception, reasoning, and general tasks. The experimental design involved comparing Thyme's performance against various multimodal large language models, MLLMs, including QWEN2, 5VL7B, and larger models like Qwen2, 5VL32B, and GPT-4o. We utilized a diverse set of datasets, including Me Real-World, HR Bench, and V*, which provided high-resolution images and complex tasks to assess Thyme's capabilities in real-world scenarios. Performance metrics included accuracy in perception tasks, reasoning ability in mathematical computations, and overall task completion rates, with specific attention to improvements in reducing hallucinations and enhancing visual recognition quality. The results demonstrated significant and consistent performance gains for Thyme, particularly in challenging tasks where baseline models struggled, indicating the effectiveness of our proposed framework.
What specific results did you achieve with the Thyme method, and how do these results demonstrate its impact on perception, reasoning, and general tasks?
The Thyme method achieved significant performance improvements across various benchmarks, demonstrating its impact on perception, reasoning, and general tasks. In perception tasks, Thyme outperformed larger models like Qwen2, 5VL32B, particularly in challenging scenarios such as monitoring and autonomous driving, where it showed over a 25% improvement in both perception and reasoning tasks. For reasoning tasks, Thyme effectively transformed complex computations into executable code, enhancing logical inference capabilities, which was particularly evident in benchmarks like MathVista and LogicVista. Additionally, Thyme's advancements in perception and reasoning led to substantial gains in general tasks, notably reducing hallucination rates. Overall, these results indicate that Thyme not only enhances visual recognition quality, but also improves the model's ability to perform complex reasoning and computations effectively.